Welcome everyone. The outline of my presentation for day 4 FDP includes paging using translation look-aside buffer, problems, problem based on segmentation, page replacement algorithms, problems on page replacement algorithms. Under paging using translation look-aside buffer, a translation look-aside buffer is a high-speed cache of page table and it tries to reduce the effective access time. We need to know few terms called hit and miss. If a required page is found in the main memory, it is termed as hit. If the required page is not found in main memory, it is termed as miss. The formula used for computing hit ratio is equal to hits divided by hits plus misses. Then miss ratio is equal to 1 minus hit ratio. In the diagram, for a logical address, the processor examines the TLB if an entry for a page is available. Suppose if an entry for a page is available, then it is TLB hit. Then the frame number is retrieved and the real physical address is formed. So, the formula for computing TLB hit is equal to TLB search time plus memory access time. TLB miss is equal to TLB search time plus memory access time plus memory access time. The meaning here is, anyway the TLB will be searched to find if a page is available or not. Suppose if a page is not available, then the page table will be accessed and finally the main memory will be accessed. So that's why here for TLB miss it has been given as 2 times memory access time. This is for page table and this is for the actual physical memory. And here using this we calculate the effective memory access time. Effective memory access time is equal to hit ratio into TLB hit plus miss ratio into TLB miss. We have already found what is TLB hit. So now if we expand this, we get effective memory access time is equal to hit ratio into TLB hit is TLB search time plus memory access time and miss ratio into TLB miss is TLB search time plus memory access time plus memory access time. So this is simplified as 2 into memory access time. So using this formula, let us see few problems. The given problem is, consider a paging hardware with TLB. Assume that the entire page table and all the pages are in the physical memory. It takes 10 milliseconds to search TLB and 80 milliseconds to access physical memory. If TLB hit ratio is 0.6, find the effective memory access time. Let us write the given data. TLB search time is given as 10 milliseconds. Then memory access time, that is access to physical memory is nothing but memory access time. It is given as 80 milliseconds. TLB hit ratio is given as 0.6. We need to find effective memory access time. Effective memory access time is equal to, we already know the formula, hit ratio into TLB search time plus memory access time plus 1 minus hit ratio into TLB search time plus 2 into memory access time. So substituting the given values in this formula, we get the following. 0.6 for hit ratio, TLB search time is 10, memory access time is 80 plus 1 minus 0.6, then TLB search time is again 10 plus 2 into memory access time is 80. So here this is nothing but 0.6 into 10 plus 80 is 90. So here it will be 0.6 into 90 plus 1 minus 0.6 is 0.4, 10 plus 2 into 80. 80 into 2 is 16, 160 plus 10 is 170. So here we get this. Then after simplifying this, we get the value as 54 plus 68 and finally after adding we get the value as 122 milliseconds. So for the given problem, the effective memory access time is equal to 122 milliseconds. Let us see the next problem. Here, a paging scheme uses TLB. The effective memory access time takes 160 nanoseconds and the main memory access takes 100 nanoseconds. What is the TLB access time if TLB hit ratio is 60% and there is no page fault? So here let us write whatever the data is given. Effective memory access time is equal to 160 nanoseconds. Main memory access time is given as 100 nanoseconds. We need to find TLB access time. And one more data is given, TLB hit ratio is given. It is given as 60%. We need to find TLB access time. We use the same formula. Effective memory access time is equal to hit ratio into TLB search time plus memory access time plus 1 minus hit ratio, the whole multiplied by TLB search time plus 2 into memory access time. So here hit ratio is nothing but 60 by 100. 60 by 100 will be 0.6. We don't know TLB search time, so I have taken this as T. Memory access time is 100 plus 1 minus hit ratio is nothing but miss ratio. Miss ratio is 0.4. TLB search time we don't know, so hence it is T plus 2 into memory access time is 100. One more data is given, effective memory access time is given. So let me equate the equation to 160. After simplification we get like this, 0.6 into T plus 0.6 into 100 plus 0.4 into T plus 200 into 0.4. So this is simplified like this, which is equal to 160. So after simplification, T plus 140 is equal to 160. Then finally T is equal to 160 minus 140, which is equal to 20. And the given unit is nanoseconds. Hence, the TLB access time is equal to 20 nanoseconds. So this is the way how to compute TLB access time using the formula. Now let us see segmentation. Segmentation is a non-contiguous memory management technique in which each process is divided into several segments of different sizes. The segment table stores information about each segment of the process. The table contains segment number, its base address and limit. And in segmentation, the generated logical address consists of two parts. They are segment number and segment offset. Segment offset can also be called as segment size. The segment offset should always lie in the range 0, limit minus 1. If segment size is greater than or equal to segment limit, then a trap or exception occurs and the physical address cannot be generated. Suppose if the segment size is less than segment limit, then the physical address can be generated. This is an overview about segmentation. Now let us see a problem based on segmentation. This is the given problem. 3 logical addresses are given. We need to find whether these logical addresses produce a trap. Suppose if they don't produce trap, the corresponding physical address has to be generated. And this is the given table. Let us see first problem. The logical address is given as 0, 430. We already know that in segmentation, the logical address consists of two parts. One is segment number and the another one is segment size. The segment number is given as 0. The segment size is given as 430. In the given problem, if you see the table, for segment number 0, the limit is given as 700. So here we have taken the limit of segment 0 as 700. The segment offset must always lie in the range 0, limit minus 1. So already we know that the limit is 700. So 700 minus 1 will be 699. Hence the segment size must always lie in the range 0, 699. In the given problem, the segment offset is given as 430. Obviously 430 lies in the range 0, 699. Hence, a trap will not be produced. Instead, we can find the physical address. So this is how the physical address is calculated. Base address and segment size are added. If these are added, then the physical address will be produced. We know the base address of segment 0 is 1219 and segment size is 430. If we add both these two values, we will get the final answer as 1649. So this is the corresponding physical address for the given logical address. Let us see next problem. Here for problem 2, the segment number is taken as 1 and the segment offset is taken as 11. So this is the table entry, segment table entry for the given virtual address. From the segment table, the limit of segment 1 is 14. We have to check for the condition. The segment offset must lie in the range 0, limit minus 1. So limit is already given in the table as 14. 14 minus 1 is 13. Here offset for the given problem is 11. 11 obviously lies in the range 0, 13. Hence, a trap will not be produced. We can find the physical address. Physical address is equal to base address plus segment offset. Base address is equal to 2300 from the given table. With this, if the segment size is added, we get the value as 2311. So this is how the physical address for this virtual address is calculated. Next problem. In this problem, the segment number is taken as 2 and the segment offset is 100. This is the corresponding segment table entry for the given segment. From the segment table, the limit of segment 2 is 100. So we need to calculate limit minus 1. What is limit minus 1? Limit is 100. 100 minus 1 will be 99. So the segment offset must lie in the range 0, 99. The segment offset for the given problem is 100. 100 does not lie in between 0 to 99. So a trap will be produced and the physical address cannot be generated for the given virtual address. So this is the explanation for the given problem. Before seeing page replacement algorithms, let us see when page replacement is done. If all the pages of a process cannot be loaded into main memory, then page replacement is done. Hence, in an operating system that uses paged memory management, a page replacement algorithm is needed to decide which page needs to be replaced when a new page gets into the main memory. And if the required page is not found in the main memory, a page fault occurs. The ultimate aim of all page replacement algorithms is to reduce the number of page faults. And here we will see the following page replacement algorithms. The first page replacement algorithm we will see is FIFO page replacement algorithm. This algorithm works on the principle of first in, first out. This replaces the oldest page that has been present in the main memory for the longest time. And it is implemented by keeping track of all the pages in a queue data structure. This is an overview about FIFO page replacement algorithm. Coming to the next algorithm, which means this algorithm replaces the page that has not been referred by the CPU for the longest time. The next algorithm is optimal page replacement algorithm. It replaces the page that will not be referred by the CPU in future for the longest time. This is practically impossible. This is because the pages that will not be used in future for the longest time cannot be predicted, and hence it is practically impossible. However, it's the best known algorithm and it gives the least number of page faults. Hence, this is used as a performance measure criterion for comparing with other algorithms. These are all the 3 page replacement algorithms we have taken for consideration, and based upon these 3 algorithms, we will see how to solve problems. Let us see how to solve a problem using FIFO page replacement. The given problem contains 3 page frames. Initially, these 3 page frames are empty. We need to find total number of page faults for the given reference strings, and we need to calculate hit ratio and miss ratio. The page reference strings given are, these are all the reference strings. 3 page frames were given. Initially, the 3 page frames are empty. These are all the 3 page frames. Initially, these frames are empty. 4 is not available in the main memory, so a page fault occurs. Now 4 has to be brought into the main memory. So it will be placed in the first free frame. Here, among the available 3 frames, 4 has entered main memory. Next, 7 has to enter. 7 is not available in the main memory, hence a page fault occurs. Now 7 is brought into the second empty frame. 6 is not available in the main memory, so a page fault occurs. Now 6 will be brought into the third empty frame. 1 is not available, so a page fault occurs. When 1 has to be brought in, the oldest page must be replaced. So the oldest page is 4, so 4 will be replaced. So now 1 comes at the place of 4. Next, when 7 is referenced, 7 is available already, so a page fault will not occur. 6 is referenced, 6 is already available. Here also a page fault will not occur. 1 is referenced, 1 is available. So here also a page fault does not occur. 2 is not available, so a page fault will occur. Now 2 has to be replaced. So this will be replaced in the oldest frame. The oldest frame is 7. So at the place of 7, 2 will get. At the place of 7, 2 will get in. 7 is not available. So a page fault will occur. Now 7 has to be brought in. The oldest page that will be replaced is 6. So at the place of 6, 7 will enter. When 2 is referenced, 2 is already available. So a page fault does not occur. Now let us calculate the total number of page faults. Total number of page faults are, let us count here, this is 1, 2, 3, 4, 5 and 6. So total number of page faults is equal to 6. Then total number of hits is equal to 1, 2, 3, 4. So total number of hits is equal to 4. Next, if we want to find hit ratio, we already know that hit ratio is calculated by using a formula, total number of hits divided by number of hits plus number of miss. So total number of hits is 4 divided by number of hits plus number of misses. So number of hits is 4 and number of misses is 6. Page faults are nothing but the misses. This is equal to 4 divided by 4 plus 6 is 10, and finally when 4 is divided by 10 we get the value as 0.4. Next, miss ratio is equal to 1 minus hit ratio. Already we have found the value of hit ratio is 0.4. So when 0.4 is subtracted from 1 we get the value as 0.6. So these are all the values for hit ratio and miss ratio. Here one thing we have to note, FIFO page replacement suffers from Beladi's anomaly, which means that if the number of frames increases, then the page fault also increases. Let us go for the next problem. Let us solve the same problem using LRU page replacement algorithm. This is the given reference string. 3 page frames are taken. The 3 page frames are initially empty. 4 is referenced. 4 is not available. A page fault will occur here. Now 4 will be brought into the first empty frame. Likewise 7 will be brought here. A page fault occurs here also. 6 will be referred. 6 is not available in the main memory. So here also a page fault will occur. Now 6 will be replaced in the third empty frame. When 1 is referred, 1 is not available. So a page fault occurs. Now 1 has to be replaced. Among 6, 7 and 4, 6 is most recently used, whereas 4 is least recently used. So in this place, 1 gets in. When 7 is referenced, 7 is already available. So a page fault will not occur, which means that this is a hit. When 6 is referenced, 6 is available. So here also a page fault will not occur. When 1 is referenced, 1 is available. So here also a page fault will not occur. When 2 is referenced, 2 is not available. So among 1, 7 and 6, 7 is the least recently used. So in the place of 7, 2 will enter. Now when 7 is referenced, 7 is not available. Hence, it has to be, some frame has to be replaced among 1, 2 and 6. 6 is least recently used. So in the place of 6, 7 will enter. Here too a page fault have occurred. When 2 is referenced, 2 is already available. So here a page fault will not occur, which refers to a hit. Now we can calculate total number of page faults. Total number of page faults is total number of miss. 1, 2, 3, 4, 5 and 6. So here total number of page faults is equal to 6. Then total number of hits is 4. If you want to find the hit ratio, we already know the formula. Hit ratio is equal to total number of hits divided by hits plus miss. So this is equal to 4 divided by 10, which is equal to 0.4. Suppose if we need to find miss ratio is equal to 1 minus hit ratio, which is 0.6. So this is the way to solve the given problem using least recently used algorithm. Let us see how to solve the same problem using optimal page replacement algorithm. Initially, all the 3 frames are empty. So when 4, 7, 6 are allocated to the empty frames, 3 page fault occurs. A page fault occurs here, a page fault occurs here, also a page fault occurs. When 1 is referred, it is not available, so it leads to a page fault. Optimal page replacement replaces a page that will not be referred by the CPU for the longest time in future. So among the pages 4, 7 and 6, 4 is not referred in future. So in the place of 4, 1 will be placed. When 7 is referred, 7 is already available. Here a page fault will not occur. When 6 is referred, 6 is available. So here also a page fault will not occur. When 1 is referred, 1 is already available. So here also a page fault will not occur. Two is not available, so it leads to a page fault. Very recently 1 has entered, so ignore it. Among 7 and 6, 6 will not be referred in the future. So replace 6 by 2. Here a page fault occurs. When 7 is referred, 7 is already available, so no page fault will occur. When 2 is referred, 2 is already available, so here also a page fault will not occur. Now let us calculate the total number of page faults. Total number of page faults is equal to 5. And total number of hits is equal to 5. Hit ratio is equal to 5 divided by 10. That is total number of hits divided by number of hits plus number of miss. Number of hits is 5. Number of miss is 5. So 5 plus 5 is 10. When 5 is divided by 10, we get the value as 0.5. Miss ratio is equal to 1 minus hit ratio. So 1 minus 0.5 will be 0.5. So this is the way how to compute the hit ratio and miss ratio. This is how the optimal page replacement algorithm works. That's all for today's FTP. Thank you all.